In the previous unit, we've just managed to understand what friction does to a flow as it goes through the combustor. Now let's get to the main part of what the combustor is used for, which is adding heat into the scramjet engine. So in order to understand how heat addition influences the flow or the Mach number, we first need to devise a mathematical model. Having done the friction mathematical model previously, it's going to be a lot easier to follow this analysis. Just like we did with the last model with friction, we now will assume again a quasi one-dimensional model of the flow with heat addition, and this is typically called Rayleigh flow. Once we do that, we are now going to again express all the governing equations in terms of one ordinary differential equation, which will be purely a function of Mach number. And finally, once we have that ordinary differential equation, we'll analyze it, solve it, and after solving it, we'll show that all the flow parameters can now be linked to the Mach number. Again, without much further ado, let's get started. As with the friction flow, consider once again flow through a pipe as shown here with a constant area pi d square over 4. Once again, before we go into the math modeling, let me review some of the assumptions we make in deriving the flow with heat addition. First assumption is steady flow as before, which gives us mass flow rate should be constant, or for this constant area duct, the mass flux m dot double prime, which equals rho u, should be constant. The second assumption we make is of inviscid flow. That is, we assume there is no friction at the fluid wall interface for this particular case where we are considering only heat addition. Third, which is what we are really after in this model, is we consider that there is constant heat addition per unit mass Q, as shown on the sketch on the left, which can be related to the change in total enthalpy Cp times delta T naught. And again, as before, we have some useful definitions of heat capacity at constant pressure. Cp equals gamma by gamma minus 1 times R, equation of state P equals rho RT, speed of sound A defined in these two forms, Mach number M equals U over A. And again, as before, after taking logarithm and differentiating, all of these assumptions and definitions can be cast in useful differential forms as below. I'm not going to narrate how we obtain each of these. These are very similar to the ones done in the friction flow model, so I would recommend reviewing that if you're not sure of how these come about. Right then, let's go back to the flow through a pipe in which we are adding heat and consider an elemental control volume like we did previously. As we can see here, on the left we have flow properties with pressure P, speed U, temperature T, and total temperature T naught entering the control volume. And then we have this gas fluid exiting the control volume with elemental increases, or small increases in each of the properties, P plus dP, U plus du, etc. Let us begin the analysis by considering the momentum balance for this control volume. As we know from before, the sum of the forces acting on the fluid in the control volume should be equal to the rate of change of momentum of the fluid in the control volume. So let us write these forces as we did for the case of flow with friction. Looking at the left hand side cross section over here, we see that the fluid enters this control volume with the pressure P acting on that cross section area. Therefore, the force due to this pressure is going to be P times A. Now, following the same sign convention that we did for the case of flow with friction, that is, any force that acts along the direction of motion of the flow is given a positive sign, and any force that acts opposing the flow will be given a negative sign. Therefore, following that convention, P times A, the force acting on the left here, is a positive force. Similarly, if we look at the exit cross section of this control volume, where the fluid is leaving with speed U plus du, with the pressure of P plus dP acting on it, but in a direction opposing the direction of flow, that force is going to be minus P plus dP times A. Which concludes all the forces we have acting on this control volume because we've assumed an inviscid flow with no friction. Again, we can see that P times A, once we multiply this, will cancel P times A and we'll be just left with the minus dP times A. Next, I'm just going to write this alongside. Let me write the rate of change of momentum. the rate of change of momentum is going to be equal to the momentum flux the momentum flux exiting the control volume minus the momentum flux entering the control volume. What is the momentum flux exiting the control volume? This should be fairly easy since we've already done it for the case of flow with friction. Let me write it at the top here. Actually, let me clean that up a little bit. Alright, so let me write this at the top here as this equals the mass flow rate m dot, which enters the control volume and also exits. Since we have the steady flow, the same mass flow rate enters and exits. Therefore, the mass flow rate m dot, which is nothing but the mass flux m dot double prime multiplied by the area A, times, this just gives us the mass flow rate m dot, times the speed with which the fluid leaves the control volume u plus du. This is the momentum flux exiting the control volume. Similarly, the momentum flux entering the control volume is again the same mass flow rate m dot, which is m dot double prime times A, multiplied by the speed with which the fluid is entering the control volume u. As we can see, once we write this down, we'll have some terms cancelling each other, and therefore when we equate the total force to the rate of change of momentum, we get minus dp times A should be equal to what was left there, m dot double prime times A times du. Let me rearrange this expression after I cancel out the areas, and I'm going to substitute for m dot double prime using equation 1 here, and I'm also going to move this dp to the other side of the equation so that we get dp plus, substituting for m dot double prime, we get rho u du equals 0. This is the momentum balance for the case of flow with heat addition. Let's call this equation 1. Next, let's proceed with the energy balance for the same control volume in which we have heat addition Q. As we can see, the energy balance will simply be the total heat added to the flow as it goes through this control volume should be equal to the change in total enthalpy of the flow. Alright, so what is that going to be? We know that total heat added, Q, can be written as Cp times delta T naught. So let me just denote that this is going to be Q, and this will be the change in total enthalpy. We'll come to that in a second, but we know Q can be written as Cp times delta T naught, and this is per unit mass. Therefore, Cp times, what is capital delta T naught? We know that the T naught with which the flow enters the control volume, that is the stagnation total temperature, on the left here is T naught, and as it leaves it will be T naught plus dt naught. Therefore, capital delta T naught, which is the change in the total enthalpy, will simply be T naught plus dt naught, which is what it's leaving with, minus T naught, which is what the fluid entered with. And we can see that we can strike this out. Alright, now let's equate this to the change in total enthalpy. But before we do that, we need to know what is the total enthalpy. The total enthalpy H, as you've learned in the earlier parts of this course, is nothing but Cp times T plus half U square. Again, this is written per unit mass. Therefore, we know that the fluid exits the control volume with certain enthalpy, total enthalpy, and enters the control volume with certain total enthalpy, and we are trying to see what is the change in that total enthalpy. Therefore, H out minus H in, which will simply be on the outgoing side, this is going to be t plus dt, and this will be u plus du whole square. Therefore this will be Cp times t plus dt plus half u plus du whole square minus Cp times T, this is what is the enthalpy entering the control volume, plus half u square. Alright, we can again cancel fairly easily this with this, but we need to do a little bit of work on this to expand it before we can cancel. So let's do that in the next step. Let me carry the Cp times dt naught here, which equals, I'm going to again take my time to write the equality sign a bit easier, equals Cp times dt, which survived there after cancellation, plus, let me now expand this half u plus du the whole squared, which is half u square plus du square plus 2 u du minus the half u square that was remaining from the previous line. Okay, we can cancel this with this fairly easily. Now we have two terms inside this parenthesis here, which is du square and a 2u du. Now I'm going to make some arguments of which of these terms is relevant and which of these terms is insignificantly small. Let me do that by beginning saying that we assume that we have a small control volume dx in which properties change from left to right but by a small amount, which means I've inherently assumed that du is going to be a small number compared to u. Let's just put some numbers so we can get our head around what is the relative significance of du square versus 2u du. Let me assume that du, because it's going to be small, is only going to be about, again these numbers are just approximate, 0.01 times, or only 1% of u. Alright, so du, let's say, was 0.01 u. Let me write out what this means in terms of the value of du square. Du square will therefore be 0.01 times u the whole square, and this will come out to be 10 power minus 4 times u square. Similarly, 2u du can be computed to be 2 times u, and using the same argument that du could be 0.01 u times 0.01 times u, which gives 0.02 times du, oh sorry, we've substituted for that, so it's going to be u square. Alright, let's compare these two quantities numerically and understand which one is going to be more important. This quantity, which was du square, is 10 to the minus 4, or 1 by 10,000 times u square, whereas this quantity is going to be 2 over 100, which is 0.02, which will be 1 over 50. So we have 1 over 50 times u square. So to compare the two, you have something that's u square over 10,000 and you have something that's u square over 50. Clearly this term is going to be much smaller compared to this term. And the same argument will hold if you choose any other arbitrary value for du small enough compared to u. Therefore, I'm going to make the case that du square is going to be a small number compared to 2u du, and it's going to be okay mathematically to ignore its effect. And so we'll do that and we'll say that goes to 0. Let me just get rid of these explanatory text on the right so we can proceed with our derivation. So we managed to take out the energy balance and make some simplifying assumptions already. Let's proceed by now cancelling the 2 with the 2, since that was the only term remaining. In the next step, I'm going to use the definition for Cp, which is this equation here, and substitute as, and I'm going to write the Cp in a slightly split form as 1 minus gamma minus 1 multiplied by gamma times r times dt naught equals, again I'm going to take the Cp and write it in the same way, times gamma rg times dt, and what was remaining from this messy expression was just the u times du. Alright, now the time is ripe to start doing some algebraic manipulation. The very first thing to do is to divide by u square, the entire expression. So I'm going to selectively place the u square under the gamma r here, u square under the gamma r here, and the u square over here. The simplest thing is to cancel the u with the u, so we got a du over u over here. Alright, and I'm going to put this way so that we know that we already did that. Okay, as we did with the case of flow with friction, we're going to start wondering why we have terms which don't resemble the differential form over there. That is, every single term in the differential form is differential of a variable over that variable. Clearly that is not the case for dt naught as well as dt. So we need to fulfill that missing part. So for the case of dt naught, I'm going to have to divide by t naught, which also means I have to multiply by t naught. And once we have this, I'm going to say, oh, look at speed of sound definition A, and in particular this form. So if you square this, a square will be equal to square root of gamma rt, and all I'm missing there is the t, so I'm going to multiply by the t, and I have to divide by the t, which I'll put down here. So I've got now gamma rt, which will be a square over u square, and then I have a t naught over t. Doing the same algebraic manipulation here, I know that I need to divide by t so that I get this differential in the form dt over t, for which I need to also multiply by t. Again, the same argument, gamma rt is a square, and you have a square over u square. A square over u square will be nothing but, in this case, 1 over m square. Therefore, the next step is obvious. I'm going to substitute here as 1 over gamma minus 1 times a square over u square, which was 1 over m square, times dt naught over t naught, times this t naught over t can be substituted for using the isentropic flow relations as 1 plus gamma minus 1 times m square. Sorry, 1 plus gamma minus 1 over 2 times m square. And this equals, again, the same. We can see again that this is a square over u square, which is 1 over m square, times dt over t plus du over u. Alright, so this looks a bit promising now, in that we've managed to eliminate some variables, and we have expressions now which are in terms of dt naught over t naught, dt over t, du over u, and the Mach numbers m square. It should be clear what we are going to attempt. That is, we need to eliminate dt over t and du over u and represent everything in terms of the Mach number, so that the entire expression will be in terms of the change in total temperature dt naught over t naught related to the Mach number. We'll proceed to do that in just the next step. Alright, for the moment let's halt our work on the energy balance, from which we've already managed to simplify into terms that are in terms of the Mach number the total temperature T naught and the static temperature T and velocity U. Next, let's look back at the momentum balance expression that we derived, which was equation 1, and start doing some algebraic manipulations so that we can now think of eliminating dt over t and du over u in terms of the Mach number. Therefore, the first step to do there is to divide by rho times u square. And when I do that, I'm going to be again somewhat selective in the way I write things. That is, the first step is going to be just dp, and I'm going to leave the 1 over rho u square over there. And of course, plus rho u du, and divide this by rho u square, which is going to be equal to 0. Okay, so the next step is, I hope by now, so beaten into our heads that it's obvious. We're missing the p, so let's multiply and divide by p. And once we have, we can also cancel rho u with rho and u. So this is in the right form, du over u. Once we have p over rho, we always cast an eye at the speed of sound expression and say, if we square this, a square is gamma p over rho. We have a p over rho, so all that's missing is a gamma over a gamma. So gamma p over rho is going to be a square over u square is going to be 1 over Mach number square. So this is again leading us to very familiar territory, which is we get 1 over gamma m square times dp over p plus du over u equals 0. Right. We managed to simplify the momentum equation down into the differential forms that we like, but again we have pressure, which is not related directly to the Mach number as of yet. To get rid of pressure, what we'll do is look at the differential form of the equation of state and say that we can substitute for dp over p in terms of this equation, which is in terms of d rho over rho and dt over t. In the next step, we'll do just that and say 1 over gamma m square multiplied by, open bracket, d rho density over rho plus dt over t, and this is done using equation 9 on the right hand side, close brackets, plus whatever was remaining, which is du over u equals 0. Alright, we're one step closer. We'll now look at equation 8 and say d rho over rho can be substituted in terms of du over u. We'll do that. And we get 1 over gamma m square multiplied by minus du over u using equation 8 plus dt over t plus du over u equals 0. Now I have an equation in which I just have du over u and dt over t and Mach number. Without showing the rearrangement, I'm going to claim that I can write this out as dt over t equals 1 minus gamma m square multiplied by du over u. Let's box this equation and keep it. It's going to be a useful equation for us. Again, the process of getting from here to here is some simple algebra which I've left for your perusal and to do work out on your own. Alright, the next step is we now have a relationship of dt over t to du over u, but I also want a relationship for du over u in terms of the Mach number. So to do that, we'll start off using the expression for Mach number dm square over m square, equation 11, particularly the last form which relates it to du over u and dt over t. Therefore, d of m square over m square equals 2 times du over u minus dt over t, and in the next step I'm just going to use what we derived just now, that is dt over t in terms of du over u and the Mach number, and just substitute in for the du over u as 1 minus gamma m square multiplied by du over u. Right, so this should be further simplified, of course, and we can write this as equal to, once we pull out the du over u, we'll get a 2 remaining in the first term, minus 1 minus gamma m square, and the whole thing is multiplied by du over u. In the last step, we're going to say, let's simplify this. This will give dm square over m square equals 1 plus, so 2 minus 1 is 1, and the minus and minus will make it a plus, 1 plus gamma m square times du. And again, I'm going to rearrange this like this and say du over u equals 1 over 1 plus gamma m square times dm square over m square. And there you have it. This is the velocity Mach number relationship derived for the case of flow with heat addition or Rayleigh flow, using these assumptions of inviscid flow as well as steady flow and constant heat addition. Again, we can see that this velocity Mach number relationship is different from that for the case of flow with friction, in which we had a slightly different set of assumptions. And so it should be clear that these relationships of velocity and Mach number are very specific to the assumptions that we have made along the way to develop them. But again, this is a very useful expression for us, and is much needed to proceed to finish the derivation and express this original equation in terms of just the Mach number and dt naught over t naught. In recognition of its importance, I'll again store this over here. Alright, having done the work on the momentum balance, we boxed an expression in terms of dt over t. On the right hand side we had Mach number and du over u. Further continuing, we also developed the velocity Mach number relationship, which is here. I'm going to set these aside for a moment and proceed working again on the energy balance equation, in which we now have dt naught over t naught, dt over t, du over u, and the Mach number. And we have said that we want to eliminate dt over t and du over u in favor of the Mach number. And the process to do that is staring at us with these two equations right here. So the first step is going to be to substitute in for dt over t using this boxed equation into here. Let's do that first. We'll get 1 plus gamma minus 1 over 2 times m square divided by gamma minus 1 times m square multiplied by dt naught over t naught. We've done nothing to the left hand side. Just substituting for the first term here, we get 1 over gamma minus 1 m square, which was there from before, and then 1 minus gamma m square times du over u plus du over u. Let's simplify the right hand side a bit more. We know we can pull du over u from both terms to get 1 minus gamma m square by gamma minus 1 times m square plus 1 times du over u. I'm just going to continue to work on the right hand side because I'm not doing anything to the left hand side as yet. Let's simplify this further. Let's take the common denominator for the 1 and this term to get 1 minus gamma m square plus gamma minus 1 m square in the numerator, and we have the common denominator gamma minus 1 m square, and this whole thing is multiplied by du over u. Again, we can see once we multiply gamma minus 1 by this m square, it will cancel. The first term here will cancel with the gamma m square, so cancel that. And then we are left with, in the numerator, just 1 minus m square divided by gamma minus 1 gamma minus 1 m square times du over u. Next step is, I would say, quite obvious by now. We have an expression of du over u in terms of the Mach number. We're just going to plug that into here. So still continuing to work on the right hand side, we get 1 minus m square over gamma minus 1 times m square multiplied by, substituting for du over u, this is 1 plus gamma m square multiplied by d of m square over m square. Alright, so let's bring out the left hand side we have ignored for so long down here and write it as 1 plus gamma minus 1 over 2 m square in the numerator times dt naught over t naught divided by gamma minus 1 times m square. For the last part, I'm just going to rearrange everything so that the variables are separated out nicely and write this as dt naught over t naught equals 1 minus m square. Oh, and I didn't point out that we could cancel the gamma minus 1 m square here with the gamma minus 1 m square. So we have the 1 minus m square remaining in the numerator divided by, once I move that to this side, 1 plus gamma minus 1 over 2 m square, and then we had a 1 plus gamma m square here. Okay, and the last term is dm square over m square. Again, like with the case with flow with friction, in the case of flow with heat addition, we are now capable of wiping our brow off the sweat and say, phew, we managed to get this expression in which we now have everything expressed in terms of the change in total temperature T naught or dt naught over T naught in terms of the Mach number m. We'll stop for here at this unit. In the next unit, we'll see if all this painstaking algebra was again worth our time, and if can this differential equation first of all give us a physical insight of what is going to happen to the flow Mach number as we add heat to the flow, and more importantly, when we solve this differential equation, are we able to express not just the stagnation temperature T naught but all other flow variables in terms of the Mach number, from which we can understand the full physical implications of what is going to happen to the flow as you add heat into it.